Hello. In this video, we're going to look at a couple of examples of ways to use prime factorization, and that is specifically to determine least common multiple and greatest common factor of a pair or a group of three or four, or however many numbers. First, I want to make sure we are all clear on what the difference is between factors and multiples. So the factors of a number are all of the whole numbers that can evenly divide that number. So factors of 6 would be 1, 2, 3, and 6, because 6 is divisible by all of those numbers. 1 is always a factor of any number. The number itself is always a factor. If those are the only two factors, we're dealing with a prime. If we have other factors, then we are dealing with a composite number. Multiples, on the other hand, are what we get when we start with that number and multiply it by any whole number. So because 6 times 1 is 6, that is the first multiple of 6. 6 times 2, 6 times 3, 6 times 4. All of these will be multiples of 6. That list can go on infinitely. So it is actually impossible to list all of the multiples of a number. But here I have the first 7 multiples of 6. As a result of which, there is no greatest common multiple between any two numbers because there will be infinitely many common multiples. That's why we're interested in the smallest of those common multiples. And as far as common factors go, 1 will always be the smallest common factor, but the greatest common factor is of interest for a number of situations. So let's consider the pair of numbers 1575 and 1617. This notation here where I have LCM and then brackets with the two numbers, that is basically telling me to find the least common multiple of those two numbers. And GCF with those two numbers is telling me to find the greatest common factor of those two numbers. Either way, I start with the prime factorization of the two numbers. So I'm going to do the prime factors for 1575 and the prime factorization of 1617. And I'm going to do the two prime factorizations in two different ways. So I'll start with 1575, which I'm going to use a factor tree. So 1575 I can see is divisible by 5 right off the bat, so I'm going to start there. 15 divided by 5 is 3, 75 divided by 5 is 15, so now I'm left with 315. Still divisible by 5, so I'm going to keep doing that. 63 is what I get when I divide 315 by 5. No longer divisible by 5, but now I can see it is divisible by 3. I'm sticking to just prime numbers. You could have divided it by 7. You could have divided it by 9 if you wanted. So this is 3 times 21, which is 3 times 7, which means that 1575 is 3 squared times 5 squared times 7. Those are the elements of that number, and they're going to be helpful in figuring out how it interacts with and combines with other numbers. For 1617, I'm going to do the latter method. I'm basically still doing the same thing. I'm identifying a prime factor and dividing it out. I just am organizing it in a slightly different way. So 1617 is divisible by 3. One of the things that is kind of a hint here is I'm probably going to have common factors with 1575. If I don't, then the GCF is just 1. But in this case, I probably think, well, maybe I'll be able to divide it by 3, 5, or 7. 5, obviously not. 7's a little trickier, but this one is divisible by 3 because 1 plus 6 plus 1 plus 7 is 15, which is divisible by 3. 16 divided by 3 is 5 with a remainder of 1. 11 divided by 3 is 3 with a remainder of 2. 27 divided by 3 is 9. That number is no longer divisible by 3 because 5 plus 8 plus 9 is 17. I am going to try dividing by 7 just to see. So 53 divided by 7 would be 7 with a remainder of 4. That gives me 49. 49 divided by 7 is 7. And I can see that 77 is 7 times 11. So in this case, 1617 is 3 times 7 squared times 11. Now, right off the bat, I can see some common factors. For example, 3 is a common factor, and 7 is a common factor. The greatest common factor is actually going to come by combining those two things together. So the greatest common factor is the product of all of the prime factors that the numbers have in common. So that's actually the easier one to answer first. GCF in this case of 1575 and 1617 is going to equal 3 times 7 or 21. The least common multiple is the combination of all of the factors of both numbers. So in order to be a multiple of 1575, at a minimum, the number has to contain 3 squared times 5 squared times 7. a multiple of 1575 will also then be multiplied by other things. And in order to be a multiple of 1617, at minimum, a number has to contain 3 times 7 squared times 11, and then it will have other factors. So in order to be a common multiple, it has to contain all of these things. The least common multiple will not contain repeats. So the least common multiple of 1575 and 1617 is going to be 3 squared, which does include the 3 I need it to include for 1617, times 5 squared. I don't need any 5s to create 1617, but I do need 2 5s to create 1575, times 7 squared. The 7 squared is coming from 1617, but it now includes the 7 that I need for 1575, times 11. So now what I can see is within all of these factors, I do have 3 squared times 5 squared times 7. I have an extra 7 and an 11, but I have at least 1575 and then a little bit more, so it is a multiple of 1575. And I have 3 times 7 squared times 11, along with an extra 3 and a couple of 5s, so that is a multiple of 1617. So the least common multiple of these two numbers is 3 squared times 5 squared times 7 squared times 11. Now, most of the time, I'm going to be okay with you just leaving that as a product of powers of primes. If for some reason you did want to expand all that out, it's 121,275. Another way of organizing these would be into a Venn diagram, where I can have the factors of 1575 in one circle, the factors of 1617 in another circle. What they have in common goes in the middle. So they both do have a factor of 3. They both do have a factor of 7. So that goes into the middle of these two circles. And 1575, in addition to having a 3 and a 7, has another 3 and 2 5s. 1617, in addition to having a 3 and a 7, has another 7 and another 11. So the greatest common factor comes from taking the product of everything that is in the intersection. So what do both of these circles have in common? And then the least common multiple will take the product of everything in all of the circles. But because I've only included the things in the intersection once, it doesn't include any extra factors. GCF and LCM can be used to solve some types of problems. So here's a couple of tile problems which can be solved using GCF and or LCM. So let's say we have a contractor who has rectangular tiles. Each tile is a rectangle measuring 12 centimeters by 18 centimeters. We want to know if I create a square, and I don't want to cut any tiles, so I'm going to tile over these rectangles into this square. I want to be able to create that square without cutting any rectangles. So as an example, I don't know if these numbers match up. They probably don't, but that's etc. And I want to be able to do a square. So in other words, along this side, this length has to be 12 times something. I'm going to call that something m, however many tiles I have. So the length of that side of the square is going to be 12 times however many tiles I have. And this length is going to be 18 times however many tiles I have in that direction. So I'll call that n, 18n. And I want 12m to be equal to 18n. In other words, I have some multiple of 12 and I have some multiple of 18, and I want them to be the same. And I want to know what is the smallest number for which they are the same. So this is the LCM of 12 and 18. For that, I'm going to consider the prime factorization. Now, these numbers are small enough that you could just list multiples of 12, list multiples of 18, and hope to find the smallest one pretty quickly. But I can be a little more efficient at that if I say, well, 12 is 3 times 4, which is 2 squared times 3. And 18 is 2 times 9, so 2 times 3 squared. What they have in common is a 2 and a 3. Yes, they have a 2 and a 3 in common. So that would be the greatest common factor. I don't want to repeat those. So the LCM is going to be everything without repeating anything, which means 2 squared. I don't need to repeat the other 2 for the 18 because 2 squared includes a 2, times 3 squared. Again, I don't need to repeat another 3 from the 12 because 3 squared already includes a 3. So within 2 squared times 3 squared, I have 2 squared times 3 with an extra 3. And I have 2 times 3 squared with an extra 2, which means the least common multiple is 4 times 9, or 36 centimeters. So 36 centimeters is the length of the side, which means that in one direction, I would have 3 tiles across, and then in the other direction, I would have 2 tiles down. A similar related problem, but slightly different. What is the side length of the largest square tile? So this time I'm saying I have square tiles and I want to cover a rectangular area. This time I know the area I want to cover. I have 48 centimeters by 60 centimeters. And I want to cover this perfectly with square tiles. Now, obviously I could use 1 centimeter square tiles and do 48 in one direction and 60 in the other, and that would work. I could use 2 centimeter tiles and do 24 in one direction and 30 in the other. But I want to know what is the largest square tile that I can use to perfectly cover it without cutting any. So the number of tiles here, the side length has to be a factor of 48. And what I am looking for is the GCF of 48 and 60. So for that, I'm going to, again, you could just, these numbers are small enough, you could probably just brute force it and figure out all the factors and find the greatest one. But 48, I know, is 6 times 8. 6 is 2 times 3, and 8 is 2 cubed. So that means I have 2 to the power of 4 times 3. And 60 is 2 times 30, which is 2 times 15. So I have 2 squared times 3 times 5. So those are my 2 prime factorizations. The GCF is what do they have in common? Well, clearly they both share a 3, and they share some 2's. What they have in common is they both have 2 2's. 60 has 2 times 2. 48 has 2 times 2 times 2 times 2. But that's more 2's than I have in 60. So they share 2 2's. So that means that the GCF is going to be 2 squared times 3. 4 times 3, which is 12 centimeters. So if I had a 12 centimeter by 12 centimeter square tile, that would still work. Anything larger would not work.